So this lesson is pretty much going to be an intuitive approach to divergence. To give a roadmap of how the entire thing is going to go, first I'm going to start by giving the intuition of what divergence represents by giving some real-world examples of vector fields and the divergence of those vector fields, and then moving on to the mathematical interpretation and how that incorporates the intuition from the real-life examples we had. So before we can actually talk about divergence, we have to understand what a vector field is. This underpins its prerequisite knowledge. So a vector field is basically what you get if you associate each point in some space with a vector, something with some magnitude or direction, and the dimensions of the space that you have must match the dimensions of the vector. So here we have an x and y, and each of these vectors is going to have an x and y component. So just to give some real-world analogs, maybe these vectors of your vector space represent the velocities of particles of fluid at each point in space, like the flow of this gas. Maybe it represents the force of gravity at many different points of space, where these vectors represent the force of gravity due to some mass, which creates a gravitational well. The well meaning like all these points flow towards it, so some point mass will flow towards the center of the gravitational well. And it could also represent a magnetic field. Basically, all these examples of vector fields, where again, each point in space defined by an x and y coordinate or a vector is associated with another vector, which is usually denoted with an I hat and a j hat component if we're working in 2 dimensions. Now, although real-world vectors like these are usually changing with time and exist in 3 dimensions, such as like a gust of wind, it's a fluid, and the velocity of those particles could be represented by a vector field, like the first example I gave. So, and a gust of wind comes and passes and moves. It's changing with time and it occurs in 3 dimensions. For the purposes of this lesson, we're going to restrict ourselves to 2-dimensional static vector fields, like the ones I showed before, just an x and y coordinate, and not changing with time. So, like I said earlier, vector fields can represent many different things, from electricity to magnetism to gravity to fluids, but when we're trying to understand divergence intuitively, it helps a ton to imagine our vector fields as the flow of a liquid. So for example, we can apply that to this. We take the vector field of the electric field caused by these 8 point charges, and then we can think of each vector as describing the velocity of a fluid at this point. So we take the vectors representing an electric field and translate them into vectors that represent velocity of particles. And here's a simulation made in Manim and Python that kind of helps illustrate this. You still have the lines from the electric fields in the back, but now they dictate, if you have a particle there, what's the force exerted and how is the velocity of the particle or the movement of that particle influenced by that. And notice that when you do this, the hypothetical fluid that results behaves in some very strange non-physical ways around some points. Here, the third point from the left at the top, the fluid seems to just spring into existence from nothingness, as if there's some kind of source or like a fountain here. And at other points, like the first and second from the top, it acts more like a sink, where the fluid seems to disappear into nothingness. And this brings us to our first definition, where the divergence of a vector field at a particular point of a plane can be thought of as how much this imagined fluid tends to flow into or out of small regions near it. So if I were to trace a circle around it, is the net flow inwards or outwards? And the divergence is defined such that the sources or fountains like this give a positive number for divergence, and sinks or wells like this tend to give a negative number for divergence. Now, if I just move this aside, sorry, and move on, you should keep in mind that a fluid doesn't have to come in and out of some predefined circle in a plane with a radial symmetry like what we saw before. It doesn't have to have a radial symmetry in order for us to calculate the divergence. In this example, we can actually see how a fluid, just to boil it down to the important parts, the fluid coming out on the right side has a greater flow, or it flows faster than the fluid coming in from the left side. And so because the flow outwards is greater than the flow inwards, we'd say that the divergence in this circle is positive, because this change in flow implies the existence of some spontaneous fluid generation or some spontaneous acceleration that goes on within here. And that's associated with, again, a positive divergence. So the way of mathematically representing this is basically, first we should understand, the notation for this is div of f, where f is the vector field and denotes the operation of taking the divergence of a vector field f. First, just to establish the divergence function, as a function, it takes in some vectors, a vector field, and it outputs a scalar quantity. And so this could be represented, and this could be represented where, again, F is the vector field, and you're taking the dot product with that vector field with the gradient of the vector field at that point, represented by this upside down triangular nabla, or sometimes I think it's called del. You know, in LaTeX it's called nabla. And this nabla, or this gradient, can be simplified into the partial derivative, into vector that's the vector that's the partial derivatives across all different components. In this case, we have 3. But know that before we were working with 2, so in our previous examples, it should be partial dx and partial dy dot f. And of course, we know that when you take the dot product between, or when you multiply, or when you're taking the dot product of this vector and another vector, you're going to get this, where you're taking the partial derivatives in each dimension of the vector field and then adding that together, x, y, and z. So we see this dot product gradient as what translates, or the divergence translates into this dot product between the vector field and the gradient. And this is outside of the scope of this lesson, but for the curl, it's a cross product between the gradient and the vector field. But the reason why this dot product exists in the first place and why this gradient comes here, like the intuition behind the mathematic behind this, we could kind of see that with this little diagram. Right? So imagine taking some small step from one point of your vector field, denoted by the vector at x0, y0, taking some step in some direction, and then finding the new resulting vector. And at this new point, the vector will likely be a little different from the one at your first point. And this is like the idea of calculus, where you're taking small differences. And there will be some change to the function after that step, which you might see by subtracting off your original vector from that new one. And this kind of difference to your function over small steps, like we learned before, is what differential calculus is all about. And this is where the gradient comes in, this is where our partial derivatives comes in. Now recall that the dot product, or just put this aside, the dot product gives you a measure of kind of like how aligned two vectors are, where two vectors that are completely perpendicular have a dot product of 0, two vectors that align completely, where the blue one is underneath the yellow one, have a dot product of 1, and if they're in opposite directions, then the dot product is -1. So again, the dot product kind of gives you a measure of how aligned two vectors are. So right now, the way that fits into this is that the dot product of your step vector with that difference vector, the step vector being blue and the difference vector being red, it tends to be positive in regions where the divergence is positive, and vice versa, where it's negative in regions where the divergence is negative. And that makes sense, because if this difference vector is flowing outwards, or if it's aligned with the step vector, and the step vector defines a circle around, then we're going to get a positive divergence because the dot product is positive. Whereas if they're facing in opposite directions, then we're going to get a negative divergence because the dot product is negative. And so, although the dot product only applies to one vector, the way that we get the net divergence for an entire circle, and we exaggerate the size of the circle. In reality, of course, since we're doing differential calculus, the circle is infinitesimally small, or an instantaneous change. And so to find the overall divergence in a region, it's sort of an average value for this dot product over the circle of all possible step directions.